in our study of thermochemistry or thermodynamics, we looked at a number of graphs so we could see how one variable affected another. The independent variable affects the dependent variable. What I want to look at now is a graph where there are really two independent variables. We're not going to be looking at how the independent variable on the x-axis or horizontal axis affects the dependent variable on the vertical axis. We're going to have two independent variables, one on the x and one on the y, one on the horizontal, one on the vertical. And we're going to look at how that affects a dependent variable that's in the body of the graph. So we're looking at something called phase diagrams. So we have already gone over reaction energy diagrams. We have already gone over endothermic, exothermic reactions for reaction energy diagrams and how catalysts affect the reaction energy diagram, and therefore how catalysts affect the progress of reaction. Why it is that catalysts can speed up a reaction. It has to do with shaving off the top of that energy hill. I want to talk about something a little bit different now. Okay? I want to talk about the effect that pressure and temperature have on phase. Okay? So if you remember when we were looking at the heating curve for water, we looked at how water went through different phases. We looked at when we heat up the ice and we got, let's see, heat being added down here and temperature over here. The heat affects the temperature. We get an upward swing. While it's melting, it flattens out. When it gets to liquid water, it heats up. When it finishes melting, then changing from liquid water into steam flattens out, and then we can heat up the steam. Okay? But that's when the pressure is constant. There's no change in pressure. Okay? What I want to look at now is what happens when we do change pressure, but it's not going to be quite the same kind of graph. Now let me say something about what we're going to be drawing here. This is a kind of generalized graph. Okay? It kind of sort of reflects the behavior of all substances. But if you were to actually graph a specific substance, it might look a little different. The curves might be a little more flattened or a little more indented. The temperature ranges or pressure ranges would be different for every substance, but the pattern in general is the same. Okay? And that's what we're looking at, a kind of generalized graph for phase diagrams. And so this is, we're going to call this a phase diagram, because we're talking about phases of matter, okay? Different phases, solid, liquid, and gas. A phase diagram for most substances, okay? What we're going to look at here is how temperature and pressure affects phase. So I'm going to put pressure over here. Now this is a little bit different than the graphs we've been doing so far. I'll explain that after I get these axes labeled. So this is going to be pressure over here. Okay? So every graph, I think every graph we've done so far, we've always said this is our independent variable and this is our dependent variable. So what we're looking at is the effect of this variable on this variable. We're not doing that here, okay? Because temperature isn't affecting pressure. It can affect pressure. We'll save that for our gas laws when we get to that, okay? Right now we're looking at how temperature and pressure affect the phase. So really we have the independent variable is both of these are independent variables. And the dependent variable is what we're going to see out here. That's a little bit different than you're used to, okay? And all the labs we're going to do, we won't do one of these like this. Every time we do a lab, it's always how the independent variable we have down on the x-axis or horizontal axis affects the dependent variable over here on the vertical axis, okay? This is a little bit different, just so you're not confused by what we're doing, all right? So for most substances, there's a behavior where as you adjust temperature and pressure, there is a range of low pressures and low temperatures where a substance never becomes a liquid. You go straight from the solid phase to the liquid phase. We're going to put solids over here, in this area of the graph, okay? And we're going to have gases down here. Did I say it goes straight from solid to gas? Liquids? I mean solid to gases, okay? I should probably just say gas, not gases, because it's not plural. It's one gas, okay, for a particular substance, whichever general substance you want to consider, okay? Solid and gas. So there is a range of low pressure and low temperature for almost every substance, virtually every substance, where you go straight from solid to gas. You don't go through liquid. Okay, if the pressure and temperature is low enough, we don't go through a liquid phase. So the fact that we have liquids on our planet means that the pressure has to be, high, relatively speaking. Okay? Water exists as a liquid on the planet only because we have atmospheric pressure. The higher you go in our atmosphere, the lower the pressure is. And the reason for that is the higher you go in the atmosphere, the less air there is above it to push down on the air below to create that pressure. Okay? So the higher you go in the atmosphere, the less air there is pushing down, the lower the pressure, the less chance you're going to have liquid water. In space, there is no liquid water. In space, there is no liquid water. Okay? So if you were an astronaut and you weren't wearing a spacesuit and they threw you out the door of the space shuttle, for example, they don't have the space shuttle anymore, they retired that, but that's the latest spaceship we had. They threw you out the door of the spaceship and you had no space suit on, your blood boils. You die. All right, that's also why in Denver, Colorado, which is much higher up than it is here, water boils at a lower temperature. Okay, because the pressure is lower. Higher up you go, lower pressure. Okay? All right. But there is a certain point where we get enough pressure and a high enough temperature that we can have a liquid. Yes?
Just wondering, like you're talking about that atmospheric pressure keeps going up. Is there technically not something that stops and you keep going through the air just keeps rising and all? How come it gets less and less as you keep going?
Okay, well, first of all, the question is, how does that all work about the air pressure piling up and creating higher pressure as you get lower? The higher up you are, the less air there is to push down on it. Okay? Anybody ever played pile-on? Guys play pile-on. You play pile-on. Mark, I can tell Markel does because he's laughing over there. All right? Well, of course, are you on the football team? No. Okay. Well, in football, you get penalized for piling on in football. Okay? You don't need. And once the guy's down, there's no reason to keep piling on. There's no reason you pile. It's dog piles. You heard of dog piles? Okay. Because if somebody makes a really good play or something, then all the team, they jump on them. That's a dog pile, okay? Well, the guy on the bottom's getting pressed down on, yeah? That makes sense? All right? The guy on the the girl on the bottom, doesn't usually happen with girls, but sometimes, I guess. I've never seen it happen with girls' teams, but I guess it could happen. Anyway, and that's probably sexist. I'm sorry if anybody's hearing that. If it sounds sexist, I apologize. I'm just telling you the truth of what I've seen, okay? Guys kind of tend to do stuff like that, okay? The more stuff you pile up on top, the more pressure there is underneath. Let's define pressure, okay? Pressure, because that might help you understand. So the higher up you get, there's less air above it in the atmosphere to push down on the air below, and the pressure gets lower and lower as you go higher. In outer space, where there's very little air, there's almost no pressure to speak of by comparison to what there is here. Okay? Was that answer your question? Okay, so let's go back now and look at, let's define pressure, okay? Pressure is force applied to an area. Okay? Force applied to an area. So if I take my finger and I push it down on this paper, there's an area under my finger where it's pressing against the paper, okay, and I'm applying force as I push down on it. If I push down harder, I'm applying more force, and so I'm creating pressure under my finger. Does that make sense? That's all pressure is. And in the atmosphere, the molecules of air are constantly hitting your body. They're bouncing off, but the force of them constantly hitting your body is creating a pressure against your skin surface, okay, or against any surface. And so it's creating pressure. All right? So going back to this then, there's a certain point where we get enough pressure and enough temperature that we can start to create a liquid. So we got a liquid in here in the middle now. Okay? And we're going to look at these boundary lines. This is called a phase boundary here. Okay? It separates solid and gas by pressure and temperature. All right? So the phase boundary for most substances on our planet, almost all the substances on our planet, phase boundary between solid and liquid leans slightly positive, slightly forward. Everybody with me on that? Okay? It can't be straight up and down. It can't lean back. It's got to lean slightly forward. Okay? I'm going to lean it forward just a little bit like this. Okay? And the liquid-gas phase boundary is always positive. The liquid-gas phase boundary is always positive, but it has a increasingly positive curve. So positive means we're going, this would be flat where there's no positive slope at all. We're going up, and as we go further to the right, as we increase temperature, it curves up. Well, I can bend this one. Curves up. Okay? Increasingly positive. Now notice I don't go all the way to the corner here. I don't want to go all the way to the corner. I want to explain something else that's going to happen here in a minute. Okay? So, if the pressure is high enough, here we are, we're going to keep the pressure up here somewhere. We're solid, solid, solid. This is that point where we're changing from solid to liquid. We're adding energy, but we're not increasing the temperature while it heats up. And then finally, we're going to be in that liquid phase and we increase temperature. Okay? So this is kind of related to the other graph. We can't put the other graph, the heating curve for water, because it's like still another independent variable. We can't do all that in one graph. Okay? You've got to think about this in more than one context. All right? So, and down here, if we keep the pressure constant, we're not going to increase up or decrease the pressure. We are increasing the temperature. If the pressure is low enough, we go straight from solid to gas. Okay? Anybody ever seen dry ice in the grocery store? Okay? Dry ice in the grocery store is solid carbon dioxide. It never becomes a liquid because the pressure for carbon dioxide is not high enough. You can create liquid CO2, liquid carbon dioxide, but you have to put it under high pressure. So the pressure in this room would not be high enough to create liquid CO2. Okay, you might put it in your car tires and get liquid CO2, but what's the point in that? Okay? All right, so there's a place right here, right where all these come together, where if I get the temperature and pressure just right, I can have a solid phase, a liquid phase, and a gas phase all at the same time at the same place. Pretty cool, huh? Okay? And that place right there, where you can have all three physical states at the same time, it's called a triple point. Okay? A triple point. All right. Remember, these are phase boundaries. It's the boundary line as we compare temperature and pressure for a substance through which you change from liquid to gas. Phase boundary. And remember, when we're going between one of these and the other, you're adding heat to it, but there's no change in no change in temperature while we're going through that phase. Okay. All right. So this is not really looking at temperature as a kind of constant here exactly. All right. Okay. Now, there's also a point up here. That's why I didn't go all the way up to the top. There's a point up here, and this is a point where the temperature for that substance, if it gets any higher at all, no amount of pressure is going to make it a liquid. Okay? So liquids depend on a specific range of pressures and a specific range of temperatures. If I get the temperature any higher than this point here, for whatever substance it is, I don't care how much pressure I put it under, it will not be a liquid. Okay? It'll be a fluid, but not a liquid. Gases and liquids are both fluids. Okay? So this is then called, this point beyond which the temperature, any higher temperature, You can't possibly have it be a liquid. This is called the critical point. Let me move it over here to one side a little bit. Critical point. So let's define critical point then. Do I need to define triple point for you, or can you? Is that good when I explained it? All right. Huh? I can. The balance between pressure and temperature, where solid, liquid, and gas phases exist at the same time. Okay? The balance between pressure and temperature, where solid, liquid, and gas phases exist at the same time. And that's not for different substances, that's just for one substance, any given substance at a time. Okay? Pick a substance, any substance. Okay? And for that substance, that triple point exists at a certain balance where the pressure and temperature allow all three phases to exist at the same time. Okay? Critical point. The temperature beyond which liquids don't exist regardless of the pressure. I know I'm kind of writing small, but I'm trying to fit it in over here on the right-hand side for you. You can write it on a separate sheet of paper. You can write it wherever you want to. I'm just trying to keep it on the same graph. Okay? The temperature beyond which liquids don't exist regardless of the pressure. Okay? So beyond this point right here, doesn't matter how much pressure we have, there's not going to be a liquid. Okay? So this stuff up here is unique. Well, it is a gas, but it's a special kind of gas. So we're going to give it a special name. Okay? We're going to call this Justin. Because it's special. No, we're not going to call it Justin. You can call it what you want to, whatever you want to, as long as you call it the right thing on the test. Okay. So this up here, once you get beyond that temperature point where you can't make it a liquid anymore, it's called a super because it's above or beyond. Okay. Supercritical fluid. Okay. Supercritical fluid. Sure. Supercritical. You know, kind of like Marcus, supercritical all the time. No, he's not supercritical. He's never critical. All right. Supercritical fluid. Any questions about that? Everybody's good? Everybody got all that written down? So do I need to write a definition for supercritical fluid?
Can you go down? I'm trying to finish.
Yeah, can you do it?
I guess.
We need to know all the information.
I got you. Let's see. the range of temperatures which a substance cannot be a liquid regardless of the pressure. Supercritical fluid, the range of temperatures in which a substance cannot be a liquid regardless of the pressure. The range of temperatures in which a substance cannot be a liquid regardless of the pressure. So now we're going to look at a phase diagram for water. Water behaves a little differently than most substances on the planet, and thankfully it does. You and I wouldn't be here if water didn't behave differently. Okay? We're going to look at why water floats when it freezes. Almost nothing else does that. Okay? When you put ice in your tea, does it float?
Yes.
Yeah? You know why? Because of this, what we're going to talk about today. Okay? Now we're still looking at temperature and pressure. So temperature is going to be down here on the horizontal axis. Remember, this is not our, well, this is an independent variable, so is the vertical axis here. Okay, this is a strange kind of graph in that sense, in that we have two independent variables here. Temperature down here, pressure over here on the vertical axis. Now, we happen to know some specific stuff about water. We know that water freezes at a certain temperature, right? We know that it boils at a certain temperature, okay? So we can actually put some values on this line, this number line for temperature and pressure here. I could say that this is going to be my number line, or the point for 0 degrees centigrade, since temperature is down here on this axis, if I wanted to. Okay, so we're going to say this is 0 degrees C. And I can have a point up here somewhere for the boiling temperature of water if I wanted to. So we'll say this is our 100 degree C point. And at 1 atmosphere, which is essentially close to the air pressure in the room, 1 atmosphere is actually defined as average air pressure at sea level around the planet. Okay, so you could say this is air pressure at the beach if you wanted to. Okay, Myrtle Beach. Now, I'm really not going to have a proper number line in the sense that my supercritical range over here really belongs way up further than this, okay? But in a general sense, I'm going to show you kind of what's happening. Now, the key and important thing that's different about water is that water's phase boundary doesn't lean forward. It doesn't have a positive slope. It has a negative slope. Okay? But it does intersect right here. Water has a solid liquid phase boundary that leans back. Now this is actually a little too far back, but it would be kind of hard to see if I were to show you just ever so slightly back. You wouldn't be able to tell there's a lean back. So I'm kind of exaggerating the slope, if you will, okay? And we still have that point, triple point, and we got a range down here where we have solid and gas, and we said that in space, when the pressure is really, really, really low, that you never have liquid water. So you go straight from liquid to gas, okay? So solid's going to be over here. Gas is going to be down here. Actually, since it's water, we have a special name for water in a gas phase. What do we call it? Steam. Okay, that's only true for water. Water's called steam when it's a gas. Now, there's water vapor in the room right now, but this is not steam in here. It's called vapor when the temperature is not at the boiling temperature. Okay? It's called steam when you're above the boiling temperature. Okay? And we have a special name for solid water too.
Ice.
Ice, very good. All
Oh
right.
my gosh.
And most of the time when we say water, we're usually referring to liquid water. Okay, but really water has three different phases. Okay? So we got that curve. Now this curve slope never becomes negative. Okay? It's always above flat. Okay? It never goes negative. Does that make sense to everybody? All right, so I'm trying to get this even with the horizontal axis. So it never goes completely flat. It's always tilting slightly up.
So they all
Hmm?
they all look the same.
Well, this is always a curve and always sloping up, and we still have that critical point and supercritical fluid. Okay? So this is our, what do you call it right here? Triple point. Okay. And this right here is going to be our, what's this called? Critical point. And what do we call this phase up here? Huh? Supercritical fluid, or in this case we would call it supercritical steam, I suppose. We'll call it supercritical fluid.
I have a question about water.
Okay, what's your question about water?
When it gets hot and like stays in my car for like a week, is it toxic?
No. The question was, you leave water in your car for a week and it gets hot every day because right now it's still kind of a tail end of summer. Is it toxic? No.
Well, is any water, doesn't water get toxic after a while?
If it's toxic, it's because something's been added to it.
Because the chemicals in the bottle and the toxic.
Okay, so you're talking about,
When it gets hot and I'm sitting outside and like it's in there for a while and I'm drinking hot water, I'm gonna die.
no.
Okay.
You're not going
That's
to
all
die
I'm
from
gonna
drinking
die.
warm
I'm not even drinking hot
water or hot water, as long as it's not so hot to cause any kind of scalding inside or something, okay?
Okay. So
All right, it might not be as good, but it's not going to kill you, okay? What?
I can drink the water.
Hmm? Yeah, sure. All right, so the question is, he's having a hard time staying awake too, so he's going to go back and wash his eyes in the eye wash, okay? Now, if there's any water splattered around it, just make sure you wipe it up, okay? All right, so that's the behavior of water. And look at this, look at this. The reason this happens is because the density of ice is lower than the density of liquid water. Because water expands when it freezes. Why do we have potholes on the highway?
Because the water freezes underneath it.
Water freezes under the surface and expands when it freezes, and it pops the top. Okay? Why do we have landslides in the mountains? Rock slides in the mountains.
The water freezes underneath.
The water gets in the cracks, it freezes, and when it freezes it expands, it breaks away the surface of the rock, and it crashes down the highway. Okay? So that's what water does. It expands when it freezes. It also means it's going to have a lower density, so it floats on top. So the little fishies can live when we got ice on the top of the water.
I
Okay.
had tap holes one time.
You had tap.
In
Uh-huh.
my house, or at my house, it's like a fountain, and it froze over, and there were like tap holes in my little thingy, and
Yeah.
they were like still alive. When
There you go. So what she's describing, for those of you listening to the recording, is she's describing having tadpoles at home. Yeah, I'm repeating it so people can hear it because you're talking. Okay, tadpoles at home, and it got cold in the house, and it froze to the top, and little tadpoles are swimming around, doing fine. Okay, it turns out I don't mention your name. Nobody's gonna know who it is unless you say so. All right. Here's the thing. The colder the water, the more oxygen there is. Cold water can absorb more oxygen. We'll get to that when we get later in the semester, okay? And so there's actually more fish in the water in cold water than there is in warm water. Yeah, because there's more oxygen. Okay? Yeah. Pretty cool, huh? All right. Now, those are our phase diagrams. Now let me be clear about something, okay? Everything we've covered since the last test could be on the test. In fact, we'll probably cover a few more things just to make sure we've covered all the details tomorrow. But we're going to be reviewing tomorrow. Remember what the rule is about reviews. If you don't come with questions, I don't review and I go on to Unit 2. All right? Got that? We'll review things like phase changes and the heating curve for water. Don't pack up yet. I still got 5 minutes of your time, folks. Slow down. All right. Okay, we're going to review the calculations for exchange of heat. That Q equals mass times specific heat times change in temperature, mass times specific heat for change in enthalpy when we're going through a phase change. Okay, we'll review all that if you want me to. Okay? But all that could be on the test. The test is Friday. All right, does anybody have any questions at this time? All right, then. Your job tonight, your homework. You're not going home without homework. Your homework is review. So, no, don't pack up right now. Get out your notes right now and start reviewing. And you can get a little head start on what you're supposed to be doing tonight. Okay?